So good morning, everybody, and thanks for coming. My name's Keith Whitwell from VMware. I guess in a previous life, our group at Tungsten Graphics spent some years developing drivers for the MESA open source stack. And in that time, we looked at lots of different hardware and brought up stacks in lots of different environments, not just on Linux, but multiple operating systems. And I guess we in that time, we covered a lot of the same ground again and again, and found ourselves wishing that there was a better way to leverage the work that we'd done in one environment in the other situations that we found ourselves. And so kind of incrementally, kind of organically, we found ourselves looking at a set of desires to build a stack that would facilitate that. So particularly come up with something that would be portable to multiple operating systems, something that would significantly reduce the effort involved in writing a driver. And the background to that is simply that the drivers that we were producing had a structure that was very similar from one piece of hardware to another. You know, we were looking at the MESA driver interface and taking that to hardware. We found ourselves either wishing we had time to implement the same components and finding we didn't have time to do them, and ending up with a less good driver as a result, or where it was absolutely necessary, re-implementing some of the same things again and again. So things like using the 3D engine to accomplish 2D tasks that GL required, but the hardware itself didn't. Bridging the gap between GL semantics and what we typically found implemented in hardware. And as we looked at piece of hardware after piece of hardware, it was clear that there's a common set of capabilities that hardware provides, and they're fairly stereotypical. And it would be possible to put an abstraction together that captured those facilities, those hardware facilities that are common, and do the work that we found ourselves repeating again and again on one side of that abstraction, and have a clean, simple environment for building hardware drivers on the other side. And really, Gallium is what came out of that set of desires. I'm wandering off my slides, of course. So what we basically ended up with was a set of components that are separated by pretty much watertight interfaces, and this facilitates our ability to reuse these components. So basically, we end up with barriers here that are impermeable to the components on either side, and that's significant because if you have an impermeable interface, you can take what's underneath it or above it and substitute an alternate component. So if you have these components separated into hardware-specific, operating-specific, and graphics API-specific components, then having those watertight interfaces means that you can take an existing hardware driver and operating system instantiation and slot a new API in on top of that. So the environment that we brought ourselves up on, and which continues to be a very important one, was the MESA OpenGL stack, and that's what's diagrammed there. Really there are two APIs of interest in OpenGL. The first one obviously is OpenGL, and the second one is GLX. And it took us a little while to realize that we needed to treat these two APIs as individual entities. Basically, until we tried to do GL on something that didn't have GLX. But this is the overview of the architecture. This is what a Gallium driver looks like, and the magic of Gallium, or the real neat trick that it does is it really enables the kind of block diagram engineering that you always see people doing, but in actual fact we're able to do it in real life. So where does this go? So I guess, yeah, so if I'm talking to the diagrams here, say we imagine we've built this hardware driver. If we'd really like to reuse that elsewhere, and it's possible with Gallium to simply, as I said, slot in a different state tracker, a different API on top of the hardware interface, and keep the whole rest of the stack intact. And because, assuming that we've done a decent job defining this interface, it really does expose what's necessary it should expose everything that the hardware is really capable of doing. Plus or minus, some 5 or 10% of special cases, and from our point of view, that's been a good trade-off. So there are some minor inefficiencies that creep in because we don't exactly match what the hardware can do, but there's enough commonality that the overall win is huge. So we end up with for the same amount of effort, we end up with a much better stack on the top that keeps more things in hardware, basically everything in hardware all the time. Versus previous cases where if we tried to build this thing from scratch, with a same given amount of effort, we'd have had to punt all sorts of things and end up in all sorts of terrible suboptimal cases, and then have to do the same thing again the next time we saw a new piece of hardware. So what do we get? We get up here a sane abstraction of hardware that is fairly stable and we can target our APIs to. Down here, we have a simple interface that we write hardware drivers to, and we get to choose at each level. Okay, so the special thing is here we have the Gallium interface. That's defined and public. That is Gallium. So Gallium is that interface. I guess people who've worked in GPUs have probably seen hardware abstractions in companies many times. They'll see an IHV will build some sort of an interface above a family of chips where am I going? Sorry. I guess what's really unique about Gallium is the fact that this interface it's just an interface. There's not a particular implementation on either side. So there's no core Gallium runtime. We just have the thinnest possible interface that we can slot everything out from on either side. So there's very little hardware dependency in there. So I think when an IHV sits down and tries to abstract over its family of GPUs, it tends to build a large chunk of code that has all the knowledge about the GPUs inside it, and have an interface on top of that. And the interface is influenced by the GPUs that they're abstracting over. I think because we've been very interested in working on both sides of that interface and being able to slot diverse hardware in and out and diverse APIs in and out, we've ended up with an interface that's less influenced by the GPUs by a particular GPU or family of GPUs. That's not to say it's the greatest interface in the world. There's all sorts of expedient stuff in there, but it has been proven to be amenable to diverse interfaces and diverse GPUs on either side of it. So and I guess the history of Gallium has really been one of expanding the scope of problems that we feel that we can solve with this thing. So initially we started off looking at things like GL, OpenVG, and considering the standard, the obvious graphics APIs, and I guess we've expanded our scope a little bit recently with things like the Xorg state tracker, which is a is a state tracker for the XDDX interfaces. So we take what comes out the bottom of the X server and have a piece of code that turns that into Gallium 3D rendering calls. So we get basically an accelerated 2D X server on any platform that has a Gallium driver. So I think, I recognize I'm running on, but I think that gives a feel for the type of problems that we try and solve with this architecture. It really is about trying to get the combinatorics to work in our favor. So if we want to build X servers and GL stacks and VG stacks on 4 different platforms, we really only have to implement 7 components, so n plus n rather than n times n, which would be the case if you were looking at each stack in isolation. And the same goes for operating systems.